Any questions on anything before we get started? I will probably answer a lot of questions in this class, in this lecture. And if you look at the schedule, there might be a little part of it will be adjusted later. So I'm going to talk about R2R DAC, which is digital to analog converter. It's a very simple structure, and we used it for the chip we fabricated in the last senior sum project. So these resistors, how many? 8-bit, right? So 8-bit is going to be 16 resistors. You saw the resistors, the raw resistors in the lab, right? But the resistor on the chip is nothing; it's tiny. And we used. There are so many different materials. A couple, I don't know how many, maybe 20 different layers of materials can use for the process, the silicon fabrication process. And one material is called N-well. It's N-type material. That can use that material as a resistor. So just drew all these rods on the chip, not the real rods, to form all the different resistance. You can form like 2K resistors within just the footprint of micrometer, a few micrometers, a few K ohms resistors. That's pretty amazing. But the resistor string is definitely not the best option for the ADC design, because we need an ADC, we need a DAC in the ADC. It's very interesting. So you'll learn it later. The goal is to design an analog to digital converter, but we do need a DAC in there. So the DAC is a resistor ring and a comparator, which is an operational amplifier. And there's another structure called C2C. It's a capacitor-based DAC structure, which consumes less power compared to the resistor version. So I'm going to introduce that structure today, and there will be a homework. I didn't update the schedule for Friday, but there will be a quiz on Friday. I'm going to move this one to here. And after the homework one is due, I'm going to give you another quiz on superposition. But on Friday's quiz, it's just circuit one fundamentals, because I just found a lot of issues. It's worth investing some time on it. It may help, the interview questions, just in case they ask you why the voltages are being added together in the op amps. You probably don't know right now, but these are just the superpositions. It helps analog as well, I think. You're taking analog, some of you are taking analog. Okay, let's just draw on the paper. First, how did you know that VL equals to V in, right? V in times R2 over R1 plus R2. Why is that? Say it again. Yeah, I'm asking like how to derive it. If I give you a question like that, derive the voltage divider. It's not serious, not law. It's just some conclusions, very simple. If I ask you to derive V out on the quiz on Friday, how to do it? How many currents do you have in the circuit? One. And the name is I. Okay. And VL equals I times R2. Any questions on that? Ohm's law, right? A current flows through a resistor, then there will be a voltage drop. So if you're in an interview, they ask you, what is Ohm's law? What is Ohm's law? Corner. Yeah, but if you say whenever there's a current flows through a resistor, there's a voltage drop. 5-star answer. It's way better than V equals I. So it's just, yeah. Whenever there's a current flows through a resistor, then there will be a voltage drop. Okay? Plus minus, because voltage drop. Okay. So VL equals I times R2. What about VI? You got two resistors, just add them together, right? So equals I times R1 plus R2. And left divide, here over here, here over here. So it's going to be VO over VI equals I times R2 over I times R1 plus R2. And cancel, right? And then VL equals, move VI here, so VI times R2 over R1 plus R2. So that's the voltage divider theory, how you derive it. Now you know if you have a circuit like this, what is V out? You're saying, hey, I plot this guy, it's a voltage divider. So VL is here, is the same voltage node over here. So here's VL as well, right? So I just need to look at this part of the circuit and what is VL? This? What's the problem of it? And that's the incorrect answer. So why?
You can't just ignore that rate because it increases the overall resistance of the circuit.
But just look at the equation here. What's the problem? So where this came from? Because I did that. I canceled the currents of the two resistors. Do they have the same current? When you are looking at that, they must have the same current in order to cancel them, right? But do they have the same current? The answer is no. The current here is larger than this one because it got split at the node. Okay, so VL is not V in times R2 over R1 plus R2 over here because of that. You probably won't be able to know that if you do not derive it from here. Now you know it doesn't work. So what's the voltage here, actually? You have to find out the overall resistance of the parallel resistor, which is R2 in parallel with R3. That's the overall resistance, right? R total. So VO is VI times what? Over. Make sense? If I put this on the quiz on Friday, ask you to derive the voltage divider theory or voltage divider's equation, could you do that? Just let you know. Second, another thing which you didn't do well in the lab. I think I have something else here. What about current divider? You can ignore the voltage source because we are dealing with currents. So here's a current. So I1 is what? I2 is what? I1 is, this is in my brain, so I just directly write it down. I1 is I times R2 over R1 plus R2. And why? I'm getting I1, but I'm not using I1 on the top, right? So R2 here. Why is that? And I2 equals I times R1, not R2 this time. R1 plus R2. Like that. Where this came from? So the voltage here, let's just label as V, let's just call it V out. Okay. So V out, so I times the overall R is I1 times R1, is that correct? Sorry, times. R is the overall R, okay, R total. I times R total here is going to be V out, or I1 times R1 is V out as well. Any question on that? Does that make sense there, Seth? So what is R? R is R1 times R2 over R1 plus R2. Right? And then you cancel R1 here, and you get I1. So I1 is I times R2 over R1 plus R2, right? So that's a current divider. It's not divider, it's just shunting the current, or dividing or splitting the current into two branches. So just do it in the same way, I times R1 times R2. You must have a question, why the overall R here equals R1 times R2 over R1 plus R2, right? I'll get into that pretty soon. Just assume this is the conclusion here, right? So I times the overall R, which is this guy, is the voltage here. Because they are the same nodes, so same potential. VO, VO, ground, ground. Okay, so that's why I, that's the overall current, times the overall resistor, is going to be the voltage across these two nodes. And it's going to be the same voltage for each branch as well, the same nodes. So I times the overall resistance, which is this, equals I 2 times R2. Here's I2, here's R2, right? And then you cancel R2. You can find out I2 equals this. Okay. So now let's take a look at why R equals. Any questions so far? For a resistor network like that, why this equivalent resistance here equals R1 plus R1 times R2 over R1 plus R2. Why is that? Why was that? How do you derive it? So you learned R equals 1 over R1 plus 1 over R2, right? But why? It's called, what's the name of the current law? I forgot. And so you get current flows into the circuit, right? I equals I1 plus I2, right? So you're not losing any current at the node. So the current flows into the node equals the current flows out of the node. It's just like water getting into here and then being split into two pipes. So I equals I1 plus I2. And I is, if you have a voltage here, for example, V. And so V over the R total is going to be I. So I just said I equals I1 plus I2. That's why V over R, which is overall I, equals V over R1 plus V over R2. Why is still V? V over R1 is I1. V over R2 is I2. So why these are V's, not V1, V2? Yeah, the same voltage everywhere. What's next? You cancel V, right? So always when you see a parallel resistor, just directly use this one. Why do you have to derive everything from the very beginning? Just directly use it. But when I look at the circuit yesterday in the lab, you asked me how to find the current or voltage in the circuit. I never use mesh. You do need to learn mesh. You do need to learn node voltage method and all the other methods. But just to show the people who are interviewing with you, like you are an experienced electrical engineer, never use that. Just okay. So I got overall voltage, get resistance. That's how I do it. So prepare for a quiz for this thing. I don't have a homework assignment for you guys. So a lot of times I never give quiz if I do not have assignment on it, because you're not prepared for that. So this is one of the exceptions. I don't think I should give circuit 1 assignments, right? You just review it, prepare for the quiz on Friday, and it's going to be, I think, 10 to 20 minutes.
Those 3 things?
Yeah, easy. Okay. All right, and then a few examples for, say, superposition. I got some examples here because there will be it's a structure for the DAC. You need to deeply understand it. The example looks like this. Yeah, these circuit 1 problems are tedious. I have to admit that. I hated circuit 1 when I was in college, and now I'm teaching that. Got motivated when I have to use it every day during all these projects I got from external partners. They're critical. The surprise how many electrical engineers don't even know why an op-amp, right? No, that's an input voltage, right? It's an input voltage. If you have a feedback resistor here, why the voltage here is equals here? Virtual shorting, right? Or virtual ground. A lot of electrical engineers couldn't answer that question. We'll get into that sooner. No, voltages are equal. So whenever you see an op-amp is amplified, let me draw it again, just in case. I was trying to save time, but actually it's wasting time. You ground it here, right? And then that's it's very interesting. And so how many people don't even know how to use an op-amp? You just let them build an op-amp circuit, amplify a very simple 1 millivolt signal from the function generator. They couldn't do it because all the symbols, all the schematics being drawn on the textbook just doesn't work if you directly wire it up on the board. They are poorly presented, and the labs are not really designed really well as well. So you see a lot of pictures like this. Okay, so what's the biggest problem? First, an interview question, right? Why is this node equals to ground, equals to 0 volts? You don't have to answer the details of it or how the negative feedback works, right? You just need to tell them because of the negative feedback. If you just grab op-amp from the lab, it has 5 nodes, right? If here's a power rail. I just connect it to the power and connect this to ground. Are they equal? See, you just couldn't answer that. After circuit 1, you just couldn't answer that. I know it's been covered in analog as well, but the circuit 1, it should have been covered as well. It can be an interview question, right? Because this is everywhere. And just don't mention if you know how to use it. You don't even know why they're equal. So whenever someone asks you why is this one, if you ground the non-inverting pin, why is this node here equals to 0? Just simply say because of negative feedback. So where is the negative feedback? It's over here. So when you're using an op-amp to amplify any signals, should you connect it like this? It's positive feedback. You don't want any positive feedback for the op-amp. Always negative feedback. Details of it, so it's going to be one full lecture on it. You know, how to derive it, why it's amplifying. There's so many things going on. But just for that interview question, just say it's because of negative feedback. RF, feedback resistor, because of the negative feedback. And if you directly use the signal, for example, on the function generator, right? And I'm trying to amplify, you can imagine you grab an op-amp, it has these many pins, you short it to 5 volts, you short this to ground, and you probe it. You probe here, and you ground the non-inverting, and you have 2 resistors, like 10K, 1K, it's okay. And then from the function generator, you just directly give a like 10 millivolts AC signal, sine wave, and because the amplification here is 10, it's 10 over 1 is 10. Okay, so you're expecting 100 millivolts. And to connect everything, it just didn't show 100 millivolts. Why is that? What's the problem with this very simple circuit? So you have to consider what for the AC signal? So AC signal, the 10 millivolts swing, so the peak to peak is 10 millivolts, right? That's how it's defined as 10 millivolts, right? Are you swinging this 10 millivolts over here, or are you swinging this 10 millivolts here, or are you swinging this 10 millivolts here, right? You have to define what? Yeah, DC offset. Here, or here, or here. What's the DC offset here? 0. If you do not do anything to it, the default DC offset is going to be 0. It's going to swing to negative voltage. So do you have a negative rail here? That's the lowest potential in the circuit. You won't be able to see any negative voltage. So what's going to happen is, ideally, okay, here's the input. Here's the output, okay? Your input is like that. No problem, you can probe it. You can show the negative voltage on the oscilloscope. You can see it. However, for the output, because it's shorted, it's being fed into the amplifier, and you do not have a negative rail here, power rail. It's the lowest potential we have is 0 volts. So it's gonna amplify here by 10 times, and it's gonna cut the negative swing. This is what you're going to see. So what you want to do to make it work?
You get negative 5 volts into the bottom instead of ground.
Yeah, or provide a DC voltage here. You can use a 5 volts power supply, a resistor, a voltage divider. If it's 5 volts, because it's very convenient when you are designing a board, you don't want too many different voltage sources, since you need different regulators, right? If you have a 5 volts, just directly use it. Then you have 100K, 100K. To divide, now it comes to the voltage divider, right? So what's the voltage here being shorted to here? 2.5 volts. So if you put a 2.5 volts here, what's the voltage here will be, the DC? Yeah, 2.5 is virtually shorted to here. 2.5 DC is going to appear here directly because of the internal structure of the op-amp. I mean, if you're asking why, you have to really design an op-amp so you know it. But now, don't worry about that. Whenever you have a negative feedback, these two voltages are almost equal. Okay, so provide a DC voltage here, the DC voltage is going to appear here. And now I can lift it. Why? Because the AC signal is feeding into here, and this voltage is feeding into the same node. It's going to lift. It's like two sources contributing to one node, and it's going to add to each other, or we can say it's superimposing to each other. Now comes the superposition. You short one AC voltage, you short the other one DC voltage. Then what? Add them together. So you got AC voltage being lifted by the 2.5 volts DC. That's called superposition. That's why superposition is so important. You have to understand superposition first, then to understand op-amp and also DAC, right? So this is number one, the most important one in circuit one theory. Okay. So now you lift it. It's a different story right now. So you lift this guy, it swings here, and you do have space to swing. Okay, so it's going to swing here, but amplified. Does that make sense? Quick review on that. But now, let's come back to this superposition problem. Here's VL. I mean, so these examples serves for the DAC problem later. So we don't care about all the voltages for each component. And I don't want to do it because it's super tedious. I'm just not going to do that for you. So we only care about V out. Why is that? Because we want to know what is VTH, RTH. To solve this circuit right now, okay, we're not solving everything. But for now, I only care about V out because I want to get the VTH. The VTH is voltage over here. If you remove the load, here's V out, here's VTH. So I only care about VTH. That's why I only solve for V out. Simplify the process a lot. So what is V out? How do you solve it? Now you have to transform your mind to superposition. What are the steps for each? Yeah. Yeah. Yeah, step by step, right? Let's do V1 only first. Short ground, short ground. Then here's the first VL you have. That's why I went through these examples and give you a quiz on Friday first. Because now you are using it. What is V out? If you use mesh, I'm going to fail you from this class. Let's do it. See? Yeah. V1 times what? Is that R3 over something or? Never enjoy a superposition procedure. That's the first time in your life you enjoy superposition. V1 only is done. That's it. V2 only. Shit, make it bigger. V2 only. So it's the short here. I got R1. V2 is here. V3 is shorted. That's second VO. And this is R3. This is R2, V2, R1. Is that correct? Let me double check. Okay, that's right. Yeah, I wouldn't do anything from here because it looks not really nice. I have to convert it into the form that I'm used to. How to convert it? So I have to start from here. It's convert into this form, right? I've started from this voltage source, V2. And then you got R2 here. Encounter R2 first. And then you got R1 short of the ground, R3 short of the ground. And what is V out? V out is voltage over R3. So here's V out. Plus minus, right? It's equivalent. That two.
Yeah.
Good. Okay. All right. So now what? Do the same thing, right? V2 this time. R1 in parallel with R3 over R2 plus R1 in parallel with R3. That's V2 only. What about V3 only? This page is number like 5. V3 only. Short V1. R1 still here. R2, short V2. R3, and V3. Still, V out. Let's convert it a little bit. So it's going to be V3, R3, and then 2 resistors in parallel. However, what is VO? What is V out? R3 and V3. So it's a voltage here, right? And a difference. Same voltage. Can I label that? Label VO as this. Yes, right? So VO here equals V3 times R1 parallel is R2, R3 plus R1 parallel with R2. So overall, VO equals all of these 3 voltages being added together. So we're getting V1 this one. So if we give some examples to the circuit, for example, R1 is $2K, R2 is $4K, R3 is $6K, V1 is 2 volts, V2 is 4 volts, V3 is 6 volts. Let's just plug in and see what's the result. Let me double check if the equations are right. I will directly give the result instead of calculating it. Waste of time. the VOs, yeah, the VOs are always like that. Right, it's always top to bottom, right? So they are the same polarity, so just directly add them together. Mm. Good question though. So these are the numbers of the values and values of the components. Okay, no problem here. And no problem here. Okay, they're all right, correct. So if you plug in these numbers in here, which is a very simple division, multiplication, addition, very simple math. So VL equals about 3.27 volts. That's based on the calculation. So the next step is verify in LT Spice. Let's do it very quickly. Show you what I do it. Just give you a quick example since you haven't done that too much in the past. So which circuit we are simulating? Definitely this one, right? And I'm not creating a symbol of it using the symbols. I just you know, code it up here. If I label it as 1, 2, 3, 4, I just 4 nodes, and this is 0. Give a title, and V1 is from 1 to 0, and it's V1 is 2 volts. Okay, 1 to 0, 1 to 0 is 2 volts. And then I'm going to do R1. So just for sure, just make sure that you know in Spice, it doesn't have to be V1 here, right? You can call it V anything, even V Mason, whatever. But just has to start with V. For a resistor, so Spice knows it's a voltage. It's a voltage source. And if it's a resistor, it has to start with R. Capacitor has to start with C. Inductor has to start with L. Okay, something like that. So R1. R1 is from 1 to 2, and it's 2K. R2 is from 2 to 3, and it's 4K. R3, no, V2 is from 3 to 0, right? 3 to 0, and V2 is 4 volts. And R3 is from 2 to 4. R3 is 6K, and V3 is from 4 to 0, and it's 6 volts. Okay, and do a transient analysis for 1 second. It's DC voltage, so it doesn't matter how long you simulate. It's going to be a line. And save it and start LT Spice. And open up that text editor file. Just, you know, you have to select the all files, otherwise it won't show up here. And just run the simulation. Okay, so when you're turning the homework assignment, you want to make it environmental friendly. You don't want to use a black background. This is a white background. So the way to do that is go to, I'm recording this video so you can come back and take a look at it, okay? Just remember, don't tell me you don't know how to change the background color. It's here, record it. And go to waveforms. Oh, not waveforms. Color scheme. Okay, yeah, color scheme. So I set it up like a white background because you can pick up background. And you know these are RGB colors, right? 255 is how many bits? That's another interval question to test you are fake. 2 to the 8th is 256, right? But why is 255? 0 from 0, right? So I have 256 steps for 2 to the 8th power. So it's from 0 to 255. You totally have 256 numbers in there, right? It's 8-bit. The 8-bit, am I wrong? 16 times 16, right? It's 256. So you just use largest number you can have over here for the 8-bit. If you give zeros, it's going to be black. So just change it to 255 for all of them. And you can even change the color, because you can see that my simulation plot so pretty and yours is so ugly, because I changed the background, I changed the, you make it thicker. You know what I mean? So yours is very thin, and the plot traces are thin as well. You just make it more, reader friendly, okay? Publishable quality like that. Definitely change it when you're for a homework assignment. You're making snapshots for a simulation. Copy and paste it to the Word file, print it out, as your assignment. And now I'm gonna, okay, so let's come back. Which one you want to probe? Which voltage you want to probe? Do you have VL? You don't have that node. Yeah, V2. V2 is going to do the job, right? So what's V2 here for the calculation? 3.27 volts. No, the moment of truth. This is not, then refund notation. I don't know. Let's see. Oh yeah, that works. 0.27, right? How do you probe it? Single click. Exactly 0.27. That's how I verify it. And make in the homework assignment, just make a snapshot. Okay. Any questions on this type of problem? Okay, no? And then I'm gonna give you some examples for the DACs. We'll start talking about DACs. Starting with the theory first. The DAC block. Block diagram. Can you buy DAC chips on the market? If this is called D0 and this is Dn minus 2, Dn minus 1, why there's no Dn? It's n bit DAC. And you need a VREF here as well. Reference voltage. VREF. How many outputs you're expecting? DAC converts digital signal to analog signal. So what are the digital signals? Sound wave? Digital signals, sound wave. Why did you learn logic? Well, just deal with binary numbers, right? So digital signals are only 1 zeros. So for each, so these are metal pins, right? So for each metal pin is a voltage node, and you can only have one. You can only have, for in digital circuits, there are only 2 different types of voltages, 1 or 0. Okay, so these lines are 1 or zeros, and these are digital inputs to the DAC, and the DAC converts that digital signal into how many analog signals? 1. That makes sense? Because the output is analog voltage. That's why you can form not perfect, but sine waves as the output, but not here, right? You need a 1 zeros combinations over here. So why is D0 to Dn minus 1 not
D0 to Dn for the n bit DAC. It have 0, and there are only n bits, right? That's n bit DAC. So this is from D0 to Dn n minus 1. So n bit DAC has how many input combinations? How many possibilities you can have over here as an input? Yeah. So there's a factor defined like this: d over 2 to the nth, and V out, which is V out here, equals, so Vref is the overall voltage times the portion. So the portion is D, which is the input word, doesn't matter what the input is. It's just a combination of the binary numbers, which is D. So D over this many combinations, which is the portion of that input, and times the overall voltage is going to be the output voltage. Okay. D is the input word. We don't know how many bits yet. It can be a byte, can be a word, can be bigger number. Okay. So example, give you example. 3-bit DAC, a 3-bit DAC input. So now at one moment, the input to the 3-bit DAC is 100. That's a binary number, 100. And Vref is given something you connect to the power supply, which is 5 volts, for example. So what is F? What is V out? F is so what is the input here? What's the input here? 100?
No. So it's the number?
Yeah. Input, right? So F is the factor is D over 2 to the nth, right? So D is 4 over, it's odd to use binary and decimal in the same, so it's 4 over 2 to the times 5 volts. It's 4 over 8. So the analog output is going to be 2.5 volts. So hot today. Wow. I couldn't wait to swim. I directly dive in the lake after the class. Drive over to the lake. I have my swimsuit in my car.
You wear goggles or do you go goggles?
Goggle. That's fine. Yeah, 5 more minutes. But I enjoyed the class. Yeah, I do enjoy it. Does that make sense here? Yeah, there will be something similar to this in the homework assignment. All right. So another question is, what's the full scale voltage output? So what's the largest voltage you can get over here? You have to think about what's the largest number you can have over here. You have all ones, right? So what is that number? Is that correct? Oh. Right? So for example, A bit. Let's do 3 bit. What's the largest number you can get? 111. 111 is 7, right? So it's going to be 2 to the third minus 1. Okay, so this is valid. So that's the largest number you can get to the input over what? Yeah. Okay, that's the portion times what? Like Bref. And this is called full scale voltage output. I miss the summer so much. It's feel like I'm still a junior faculty member, but I'm having a life like a retired person. And
coming in 1 day a week, stopping and making sure we didn't burn down the building, and then going.
that's what I did.
I know.
And even for now, I think I'm doing a pretty okay job, right? But still, for Wednesday, I don't have one class. I didn't do anything I did something else in the morning and just came over at 1 p.m. And after 55 minutes, I would leave. 55 minutes per day, but Tuesday was very busy for the lab, right? But on the first day was busy, but based on my possible experience, you guys will run really independent in the future because the tutorials was pretty good, and the students were just following the tutorials and making all the layouts. I sit there, kind of work on my stuff, just answer questions. It was still very easy. It's so hot. That's the only downside of it. Yeah, only 1 minute left. So I don't know if you guys are ready for. It's pretty much ready. I'll probably continue working on some examples, so we'll be fully ready on Friday. So I'm going to move that homework assignment. I'm going to delay it. So see, you should be able to do it today, but I don't think so. I'll just make you feel better. Yeah, I know, but I'll probably move it to Friday, so you don't have to start it today. So Friday will be a quiz. Again, okay, very clear. You know what is that, and I will give you more examples so you can start working on the homework assignments on Friday. That's it. Nothing else. The lake, okay, the lake, it's not raining. Yes.